Okay. And let me share this calculator screen with you and show you exactly what I'm talking about here. All right. So we want to calculate, number one, this confidence interval. So what I want to do is I'm going to calculate the standard deviation. Now remember, actually, I'm not sharing the screen, am I? Sorry about that. Okay. So let's go back to that problem one more time, the one that we were just looking at. All right. So once again, the population parameter is 0.275, and our 58 divided by 200 is our sample proportion, 0.29. Okay? So I just want to say that one more time. So stop sharing and go to the calculator. This is a TI-84 calculator, but again, it doesn't matter. I'm just showing you a calculation. Now, what I want to do is find the standard deviation. So I'm going to take the square root, and I'm going to type in here P times 1 minus P divided by N. Now, what is P? That's the population proportion. That's our parameter. I'm going to type in 0.275. And I'm going to multiply that by 1 minus 0.275, 1 minus P. And then I'm going to divide by 200, which is our number of people in the sample. Now, if I enter this, that is the standard deviation. Now, what I want to do is multiply that by 2. I take 2 times the standard deviation. So I'm going to multiply that by 2. And this number here is the margin of error, 0.063. And then what I'm going to do, I'm going to take the sample statistic, the sample proportion, which is 0.29, and I'm going to subtract that number. Enter. And I'm going to take 0.29 and add that margin of error, plus, and I'm going to scroll back up so I get to that number. Enter. Now, what I've just created are the 2 endpoints of the confidence interval. The lower endpoint, if we rounded this number to 3 decimal places, it would be 0.227, and the upper number here is 0.353. So 0.227 is the lower endpoint, and the upper endpoint is 0.353. So what I've just done here is created what's called a 95% confidence interval, where we're saying that we're 95% confident that the true population parameter is between 0.227 and 0.353, which of course it is in this case, right? It is, because what is the true population parameter is 0.275. Well, it is in between these two numbers, okay? It just happens to be. It doesn't have to be, but it happens to be in this case. All right, so we're saying we're 95% confident that the true population proportion is in between these two numbers. Now, we're not saying there's a probability that it's in between there, because it's either in there or it's not in that interval, right? In this case, it is. We're saying we're 95% confident. Now, what do we mean by that? What we mean is that if we did the sampling process over and over again, maybe 1,000,000 times, we would expect 95% of those intervals that we would create, just like what I just did here, what contain the true population proportion, and 5% wouldn't. That's what we mean by 95% confident. We're not 100% sure the true population proportions in this interval, but we're 95% sure that it is, right? I hope you sort of get the idea of what we're doing. We're taking the sample data, and we're creating an interval of possible values, and we're saying that we believe we're 95%, we have 95% belief that this interval that we just created contains the true population parameter, and this is a way of estimating it. All right. Now the 0.275, by the way, typically is unknown. We don't know it. We don't know the population parameter. We're estimating it. So if we were actually going to do this square root formula, we would probably have put 0.29 in here instead of 0.275, because that's the only other number that we know. But as you can see, this is not something, this is a more complicated thing. This is something that a regular statistics course does. They do calculations like this, but we're not going to do it in this class. We're going to use the computer to do what's called simulation. We're going to simulate this sort of thing. What simulate means is we're going to sort of copy this sort of process without actually using a calculator. All right, we're going to let the computer do all the work. And that's what the stat key is all about. The stat key is going to do something like this without you having to do pretty much anything. All right, I mean, it's pretty much very, very, you just have to learn how stat key works. That's all. It's and you don't have to know all the mechanics of it, just a little bit about how it works. But anyway, this is in essence what a confidence interval is. It is a range of values which estimates the true population parameter. It's a range of possible values, and we're hoping that the true population parameter is in that range. It's in somewhere in between these two numbers, 0.227 and 0.353. All right, so I just wanted to show you the calculation so you understand exactly what we're not doing, all right? But you need to sort of understand it in a sense so that you understand what a confidence interval is, all right? That's why I'm showing you the calculation, so at least you know what the heck we're doing, what type of process we're trying to do. Now, let's go back to that book. All right. And let's go into the section called Understanding and Interpreting Confidence Intervals in this book here. All right. So we can let's read what it says here. We can use a sample statistic to estimate a population parameter, but we know that sample statistics vary from sample to sample. That's the sampling variability I was talking about. Because of this variation, we usually give a range of plausible values. That's what I showed you with the calculator for the population parameter rather than a single best estimate. All right, so we show a range of values. We call it an interval of values. Whether we are using a single best estimate or a range of plausible values, the first step is to correctly identify the parameter that's being estimated. All right, and the problem that we just saw, the parameter that was being estimated was the population proportion of people 25 years or older. And what was that? Did somebody describe what the population was again in that problem? Let's actually go back to it. Can anybody remember what the problem said? Anybody?
I think it was something about like people 25 or older with like a degree or something like
That's
that.
right, college degree or greater. Yes, that's it. So that's what they mean by you need to know what we're estimating. We're estimating the proportion of the US population 25 years and older, right? Who earned a college degree or higher, right? That's what they're referring to here. That's identifying the parameter that's being estimated. So you have to be that specific, all right? And so we have to identify the population and then what we're measuring about the population in this case. All right, everybody clear on that? So very good. That's exactly the answer to that question. All right. Now, once again, here are the things that we're going to be estimating. We're going to be estimating P, the population proportion. We just saw a question like that. We're going to be measuring also or estimating the true population mean if we're measuring something like height or weight. And we're also going to be doing these two things. Suppose we have two populations and we want to know the difference in their proportions for the same thing. All right. So for example, the question that we just looked at, the proportion of US adults 25 or older, suppose we talked about adults on the East Coast versus adults on the West Coast of the United States. All right. So suppose we have two populations that we're comparing these proportions. One thing that we could do is look at the difference in the proportions to see if there's any difference between US adults on the East Coast and US adults on the West Coast. So we could take the difference between their proportions and see if there's any difference in them, any significant difference in terms of the proportions. We could do the same thing with means also. We could look at two different groups and see if the mean is different between the two groups. Okay, so we're going to do both of those things. And how do we estimate the difference in proportions between two groups? We look at the samples for those groups and we subtract their proportions. And same thing with the means. We take these sample statistics and subtract. So we're going to have two samples in this case instead of one. We'll have a sample for group 1 and a sample for group 2. Okay, and then we subtract their means or subtract their proportions to estimate the difference in proportions or difference in means. And again, I'll show you examples of that next time. What we're going to spend our time today doing is these first two things. All right, estimating a proportion and estimating a mean. All right. So that's again something I wanted to show you, because sometimes without this book, by the way, sometimes when we're trying to teach this to your class, we go right into StatKey, and then people, I'm sure, are baffled by it. They just don't know what the heck they're looking at. I've seen that before. And no matter how much we explain it to students, they're still baffled by it. But if I hope using this book, which is the book that was used by the people who created StatKey, this will be helpful to you in understanding what we're trying to do. All right. So we're trying to take the statistics here that we're getting from samples and to estimate the parameter, the population value, all right, the population proportions, population means, whatever we're trying to do here. One of these four cases. So whatever we're going to be doing with StatKey, with confidence intervals, it'll be one of these four cases right here. Now, this last one, correlation, we're not going to do that. All right. You have enough to do just with these four. All right. Now, what I showed you before was how to create, with the calculator, I was showing you how to create confidence intervals, construct them using this thing called a margin of error. And what was the margin of error again? It was for a 95% confidence interval, it was 2 times that square root formula. And then we added and subtracted the margin of error from both from the sample proportion. If you remember, that's what we did. All right, and that's how we constructed this interval. We used that procedure to do that. We're not going to use that procedure with StatKey. We're going to use something simpler than that, actually, and we're letting the computer do all the work. So it will calculate the confidence interval for us without going through this process of creating a margin of error. We're not going to be doing that. All right. So the margin of error is used in traditional statistics through formulas to create these confidence intervals. All right. All right. And here's another example of that. Percent of Americans saying that a television set is a necessity has dropped dramatically. In a nationwide survey of 1,484 people, this is our sample size. Ages 18 and older, remember this is just the age, it's describing the population, right? These are people in the US who are 18 and older living in the continental US. Continental US, for those of you who don't know what that means, continental US means in the mainland, all right? It will not include parts of the United States that are not part of the mainland. So Alaska and Hawaii would not be considered the continental. At least I don't think so. I might be wrong. But anyway, it says only 42% say that a television set is a necessity. So in a survey, 42% say that a television set is a necessity rather than a luxury. This is our sample statistic here. All right, now they don't give you any information about the population because, to be honest with you, it's unknown. It's unknown. We don't know what the population percentage is. But we use a survey and we came up with 42%. Now, if you used your calculator and multiplied 1484 times 0.42, which is 42%, you get 623.28. Now, you know that it was the number of people who answered the question that it's a necessity is not 623.28. There's no 0.28. There's a whole number, right? So most likely it was 623 people. So really 623 people out of 1484 answer the question it's a necessity rather than a luxury to have a television set. All right. And if you take 623 and divide it by 1484, it comes out to 0.4198, which is rounded to 0.42. All right, so now we know it's probably 623 people. All right. It says here, the article goes on to say that the margin of sampling error is plus or minus 3 percentage points. There's the margin of error. 3 percentage points, which, by the way, converted into a decimal is 0.03. So how do we create the range of possible values here? We take 0.42, we add and subtract 0.03. When we subtract it, 0.42 minus 0.03 is 0.39. And when we add it, 0.42 plus 0.03 is 0.45. So between 0.3 and 0.39 and 0.45 is the confidence interval. Okay, that's what they're showing here. Everybody clear on that? That is the traditional way of doing it. This is the traditional way. This is not StatKey. Just want to show you another example of this. All right. So this is how they do it. All right. Now they already calculated for you the margin of error. You didn't have to use the square root formula and multiply it by 2. They already gave you the margin of error. So you simply added and subtracted it. All right. So you should know how this is constructed. All right. It's not that we're going to be doing it in class, but you should know how this works, how this is constructed. All right, so this is the traditional way of constructing a confidence interval. So using a margin of error gives a range of plausible values. There's your formula, general formula, sample statistic plus or minus the margin of error. Okay. We want that margin of error to be as small as possible. It says here it reflects the precision of the sample statistic as an estimate, right? So the range of values, the more narrow those range of values, the better that sample statistic is that we actually get in estimating the population parameter. That's the whole idea. We want this range of values to be small, okay? As small as possible. And then they give you a little exercise here where they give you the sample proportion and they ask you, here's the margin of error, please create your confidence interval. So you add and subtract the margin of error from this 0.54 and you get a confidence interval for part A, and you do the same thing for part B. All right, so that's all there is to that. All right. Now, how do we do this with StatKey? Let me show you, go to the next section here, constructing what they call bootstrap confidence intervals. And this is what we're going to be doing. Now, don't be afraid of the word bootstrap. I don't know if you've ever heard of the term, the saying, a person should pick themselves up by their bootstraps. Anybody hear that before? Can then somebody unmute and tell me that they've heard that term before? People need to pick themselves up by their bootstraps. Anybody hear that? Maybe it's not something. Yeah, go ahead.
I've definitely heard like my dad say it or my grandfather.
Yeah. Do you know what they mean by it, by the way? They say that?
No clue, honestly.
No clue? Well, what they mean is that you should be self-motivating. You should, in other words, if something happens to you, you should just pick yourself up and just keep going. Pick yourself up by the bootstraps. They in the old days, even way before maybe way before your grandfather was born, they had these boots on and they had straps. So you pick yourself up by the bootstraps, which means you fell down and you just pick yourself up and keep going. So if things don't work out, you just keep going and keep trying. That's what it means. So bootstrapping has this idea that we need to, if we run into difficulty creating confidence intervals, for some reason we don't meet the criteria for doing them in the way that I was showing you, don't give up. There's another way of doing it. All right. So that's what they mean by bootstrapping. All right. So that's what they mean. That's probably, hopefully that's what they meant when they were talking to you like that. So bootstrapping. Instead of using this procedure, this construction procedure I showed you with the calculator, we're going to be doing something else. All right. And I want to use an example of bootstrapping with, let's go back. We're going to do proportions first. Let's go back to what we were just looking at a minute ago. Let's look here and let's find that last example we were just working on. Let's see if I can. Let's see. I want to find that proportion question. All right, let's just find one of them. Yeah, this one here. So let's use this one here. The sample size is 1,484. And our proportion, our estimated sample proportion is 0.42. All right, so that is our sample proportion. And we know that when we multiplied 0.42 times 1484, we got, what was the number? We got about 623. So let's make 623 people the number of people who say that they think tele-TV sets are of a necessity. All right. So I'm going to use this example as a demonstration of how to use StatKey to do confidence intervals through what's called bootstrapping, and I'll explain what that is in a second. By the way, the videos that I showed to you earlier also indicate bootstrapping, this bootstrap confidence, and it shows you exactly how to do it. I'm going to show you now the StatKey. All right, so let's see if I can find StatKey here. Here it is. Show you this. All right, now here's the main StatKey screen, and in the middle here it says bootstrap confidence intervals. So this is where we're going to create our confidence intervals, and I'm interested in for a proportion. We're going to do a confidence interval for a single proportion first. I'm going to click that. So we get this particular screen here. Now, I'm going to actually create for you the example. Now, it gives you a default example here. It gives you sample size. If you look on the right here, original sample says sample size is 100. The count, this is the number of people who are answering a question one way or the other. All right, so in this case, 52 out of 100. We divide those two numbers, we get a sample proportion of 0.52. All right. Suppose I want to change it to this example we just looked at. So I'm going to do edit data here. So you can see on the left here, right under the StatKey button here, you can see there it says edit data. So I'm going to create my own example. And I know the sample size is 1,484, so I'm going to put 1,484 there. And then I'm going to put 623 as my count. That's the number of people out of the 1,484 saying the TV is a necessity. So I'm going to put 623 here. Notice that when we do this in StatKey, we have to actually put in our count. We can't put in the actual proportion. We let the calculator or a computer do that for us, and click OK. And as you can see here, it gives us our count. The count that we put in, 623, puts in our sample size, and it calculates our proportion as 0.42, and that's exactly what we want. All right, so there it is. There is our sample. All right. And now, what we're going to do is I'm going to demonstrate to you how bootstrapping works. Now, if this was really a survey, we had 1,484 people in the survey, we would ask each of the 1,484 people that question about TV sets, whether there was necessity or not a necessity. All right, and 623 said yes. But every time we ask a person this question and we're done with the survey, they cannot be resurveyed, right? That makes sense, right? You don't want to like say, all right, I just surveyed you, but there's a chance I might call you again and ask you the same question. That's stupid, right? We wouldn't want to do something stupid like that. We're not going to bother people like that. We're not going to ask people the same questions over and over again. So we are going to ask them once and then they're out of the sample. So once we ask the first person, had them answer that question plus other questions we might ask, we're done with them, and there's 1,483 people left after that first person was interviewed. Does that make sense? Now, because StatKey is not doing this process, creating these confidence intervals in the same way as I showed you with a calculator, it's using a different way. And the way it does it is it creates these other samples called bootstrap samples, which are created from the original sample. Now, how are they created? Instead of having a person not being used again after they've been surveyed, a bootstrap sample says, all right, we're going to put that person back into the pool of 1,484 people, and then we're going to choose at random 623 people with the chance that we could end up choosing the same person again. So it's possible with these bootstrap samples that we could have the same person being asked that question again. Now, we're not interviewing people when we do bootstrap samples. I have to make this really clear. This is called computer simulation. The computer is taking the answers to the original survey. There's 623 people saying yes to the question, are TVs a necessity? And the rest of them, right? There's what is it? 861 are saying no, it's not a necessity. We're taking that data and we're just over and over again, we're creating these bootstrap samples where we can theoretically ask that same person that question again. Now they're not being asked. We're just, that person is actually being pulled again and we're recording their answers again. All right, does that make sense? We're giving everybody who's chosen is put back into the pool of 1,484 people, and then we're choosing 623, or excuse me, we're putting back into the pool, and then we're choosing people at random again. We know their answers. Each person, all 1,484 people, we know their answers, yes or no, to the question. It's just we are now what's called resampling. We're taking the 1,484 and resampling. And resampling means it's possible that a particular person that's chosen could be chosen more than once. So we get these bootstrap samples, which do not look like the original sample because of the fact that some people will be chosen more than once and some people won't be chosen at all. It's possible. And how does the computer do it? Randomly. It just randomly selects people. All right. So I'm going to choose one of these. And the way to choose a bootstrap sample is I go to the left here and it says generate one sample. I'm going to generate one of these samples. And notice here the dot shows up on the graph here. See it down here? And it also, the bootstrap sample is indicated here. Now notice now, out of the 1,484, 618 are saying yes, and the others are saying no. So fewer than the 623 are saying yes now. Why? Because some of the no's, there's now more no's that are being chosen more than once in the bootstrap sample. All right, we mix everybody up and we choose people again, and it's possible that a no that was chosen before is being chosen now twice or three times, whatever. Okay, so the bootstrap sample is this resampling process can come up with a different count than before, because now there are more no's than they were in the original sample. So there are fewer yeses showing up. And then let's choose another one. Now, here's another dot showing up. Notice in this case, 640 out of 1484. It's more than the original sample, which means now some of the yeses are being chosen more than once. So I hope you get the idea that this resampling process allows us to create additional samples. All right, additional samples with new information in them, different information in them. And what we're doing is creating variability among the samples. So each of these dots represents a sample of 1484 with different counts. And the original sample, we're treating it as if it's a population. This is the point. We're treating this original sample as if that's the population. And then we're creating these bootstrap samples, which are derived from that original sample by doing this resampling so that we can get different counts for each of these samples. Now, we can generate 10 of them at once. We can generate 100 of them at once. We can generate 1,000 of them at once. Right now, because I click these buttons, I have up here, it says the number of samples. See it up here? Samples is equal to. That's the number of samples I chose, 1,112. I chose 1, 1. I've chose 110, 100, and 1,000. That's 1,012. I can choose another 1,000 if I want to make it 2,112. So let's stick with that one. So each of these dots here in the main chart here represents one of these bootstrap samples. Notice if I run my cursor over one of these dots over here, it changes what you see on the right there for bootstrap sample. Notice it says 644 for a count. And if I run my cursor maybe down here, notice it changes to 619. And notice it just changes as I move from dot to dot. Everybody see that? So whatever dot my cursor's on, it gives me the bootstrap sample. Now, once I'm off the dots, by the way, it's giving me the very last dot that I had my cursor over. So that's the significance of that. It doesn't really matter what that number is anymore because it is basically where I put my cursor over. All right. So how many dots do we have here? We have 2,112 dots. Each dot is a bootstrap sample. Each bootstrap sample has 1,484 people in it. And each of them has a sample proportion. So we're treating the original sample as if it's the population proportion, and then we have the sample proportions for each one of these dots. So there's many sample proportions here. And what we're doing is we just created what's called a sampling distribution. We've created 2,112 samples of size 1,484. And each of these dots represents the proportion of that 1,484 people in the sample who said yes to the question, our TV's a necessity. All right. Any questions about what we just did, what I just created here? All right. Now, how do we create a confidence interval? Now, the first thing we're going to do is I'm going to click this box that says two tails here because we want to create an interval. And when I click this two tails here, notice what happens. I've created an interval in the middle here, right? Interval in the middle between these two values, 0.395 and 0.444. And then I have a left tail of dots that are not part of the interval. They're in red. See how they're in red? And there's a tail of dots that are also red that are not part of the interval. Now, how did it come up with this? Well, basically, I created what's called a 95% confidence interval. Now, in this case, 95% of the dots, how many dots are there? 2,112. 95% of those dots are going to be the dots in the middle, the black dots. All right. And if I simply calculate 2,112 times, we do this also by 0.95, it says 2006.4. So about 2006 of these 2012, and that's not right. That can't be right. 2006. Yeah, that's right. So about 2006 of the 2112 dots are these black dots. All right, so that's how it does it. It does it very simply. It just takes the 95%, the 0.95, and multiplies it by 2112, and it gives you the number, approximately the number of black dots here that are in the interval. And then it determines what the smallest value of these black dots are, and the largest value of the black dots are, and this is the confidence interval. This is how it does it. All right. So this 95% confidence interval, notice it's done completely differently than when we did it with our calculator before with the traditional way of creating a confidence interval. Notice in this case here, we created all these dots, and then a 95% confidence interval is just 95% of the samples. 0.95 times 2112 gives us the number of black dots. And by the way, the number of red dots would be the remaining dots, right? So if there's 2006 black dots, that must mean there's 96 red dots. All right, everybody clear on that? And then, so what we've done here through what's called simulation, computer simulation, is we've come up with a confidence interval, a 95% confidence interval, okay? And it's from 0.395 to 0.444. Now, does anybody remember when we did this originally with our calculator? Let's actually go back to the calculator for a second. Let's see what our answer was using the traditional method. Let's stop sharing here. We'll go back to the calculator. And our original answer, all right, for the 95% confidence, was this the same problem? This is, no, this is a different problem, right? This is a different problem. So let's actually create a confidence interval using the traditional method. Okay. Sorry about that. That's not what I wanted to do. So we want to create our standard deviation. I'll just show you how we do it with the traditional method. Okay. And 0.42 was our sample statistic. So it's 0.42 times 1 minus 0.42. Sorry. Let's do it again. 0.42 times 1 minus 0.42. Those parentheses. Remember, we divided by the sample size, which is 1484. Hit enter. Now we multiply this by 2. That's what we did before, if you remember. And then we took our 0.42 and subtracted that number that we just got. And then we took 0.42 and added the number that we just got. All right, so if we rounded these to 3 decimal places, we would get our confidence interval was 0.39 to 0.45, right? That's what we got through the traditional method. Now let's look at Stackey through the so-called resampling method that we just talked about. Go back to Stackey. And look at the answer. Boy, that's close, isn't it? That's so close. 0.395 to 0.444. Actually, this right endpoint is very close to what we got through the traditional method. So look at this. Without actually using formulas, we came up with a confidence interval very close to the confidence interval that we came up with using the traditional method. All right? And did we do any calculations here? Didn't do any calculations. We calculator, the StatQ program does it for us. Now, what a big advantage of the StatQ program is we can change the confidence level. Remember, we said 95% confidence interval. The 95% remember refers to what's called a confidence level. What do we mean by confidence level? It means if we run this, whatever process we're doing over and over again, we expect 95% of the samples to contain the true population proportion. Okay? We can change this now to another percentage. Let's suppose we wanted to do a 90% confidence interval. So what we do is we just click in the middle here, and I'm going to change this to 0.9. Okay, 0.9. Click OK. And now I've created a 90% confidence interval. Notice what happens when we do that, by the way. The interval now becomes more narrow. If we reduce the level of confidence, we now have a more narrow interval, which is what we want, by the way, a more narrow interval. But we've given something up. We've given up level of confidence. Now it's possible there's out of all the 2,112 samples here, we now have 10% of them that are outside of the interval instead of 90%. Instead of, in the previous example, 5% being outside the interval. 90% of this number here, we calculate it, 2,012 times 90%. We now have about 1,901 of these black dots. So we have a smaller number of black dots, and we have a larger number of red dots. The red dots are just 2,112 minus 1,901. So the interval becomes more narrow. So this is one of the things that you need to see, is that as we lower the level of confidence, we make this interval more narrow, which is a good thing to make it more narrow. All right. And then if we raise the level of confidence, let's change it now to 0.99. Okay. Notice the interval becomes wider now. Now more of the dots are black, more of the dots are in the interval, and we end up with a wider confidence interval. Okay. So this number in the middle here is the number we can change. We never change these two numbers here. Okay. We only change this one in the middle for our level of confidence. And we create this number of samples. Now you could just use these here to create the number of samples that we need. All right, so if I ask for you to create 3,253 samples, just use these here to create the 2,300, we can't create that number of samples, all right? You can do that. If I need 3,000, it'd be, you click this generate 1,000 samples 3 times, and if you need another 300, you click 100 samples 3 times, like that, until you get the number that you want. And by the way, if you make a mistake, you can always reset and start again. And because this is computer simulation, if one of you does this plot exactly the way I describe it, this particular one, and I do it, we're going to get answers that look different. They're going to be different looking, all right? But not too much different, but they will be different because it's computer simulation. It means that these things are being done randomly. We will get slightly different answers to the question. All right, but this is how you create confidence intervals. And the way and what I'm going to do next time is I'm going to show you the other 3 types of confidence intervals. I'll give you examples of all 3 of them. And then I'm going to show you how to interpret them, all 4 types. All right, that's what we're going to do next Tuesday. Is I'm going to show you how to create the other 3 types of confidence intervals. And then we're going to do interpretations, and I'll show you exactly the questions I'll be asking on quizzes and tests. All right, so there's no confusion about any of this. All right, any questions? What I've done so far? And by the way, you can go in StatKey and you can play with it. After you've watched those videos, go in and play around. You can't break it. Just follow what I did in the in here, and you create your own examples if you want with proportions. You can change the sample size. You can change the number of people say yes to a question, whatever. And just play with it until you become familiar with it. That's how you learn, by the way. You don't, when you study for tests, this is not like the history test where you study and memorize stuff, all right? You need to actually play around with the software, become familiar with it, and ask questions. That's how you learn. All right, any questions? All right, so I'm gonna stop this recording. Now remember, there's gonna be 2 recordings this time, part 1 and part 2, because I had to stop the recording to exit out just for a minute. So I'll stop